The purpose of this lesson is to discuss an important idea known as the First Law of Thermodynamics, and also to talk about something called the internal energy of a system. If you think about, let's say, a gas, it's made up of tons of molecules moving around, bumping into each other. There's attractions, there's repulsions, and all those different molecules and all the forces they put on each other, those result in lots of kinetic energies and potential energies. And collectively, all that energy is referred to as internal energy. The AP equation sheet calls it U. Your textbook calls it E thermal. The important thing to understand about how you change those energies is you could do two things. You can add or subtract heat from a system, or you could do work on a system. And the sum of those is ultimately going to change all those energies we collectively call internal energy. This important equation is known as the first law of thermodynamics. And it looks a little unfamiliar, but it's closely related to the idea of conservation of energy, EO equals EF, that you've previously learned. So in this lesson, what I want to do is take EO equals EF and use it to derive the first law of thermodynamics. And that way you'll see kind of what assumptions are made and how we arrive at this equation. What I'd like to do first is I'd like to start with an equation we all are pretty familiar with. Energy original equals energy final. So in Physics A or AP Physics 1, what are the types of energy we primarily focus on? Potential and kinetic. So I'm going to write potential original plus kinetic original equals potential final plus kinetic final. So as you guys have read chapter 11, I hope you guys have seen that there's another kind of energy they talk about, which is the internal chemical energy, which they call thermal energy. That can be present just in the molecules themselves. So I put ETH original and ETH final, energy thermal original and energy thermal final. And ultimately what I want to do is I want to try to expand this out to include the ideas of work and heat and everything like that. So I'm going to rewrite this. And what are the two ways that we can transfer energy in and out of a system? Work and heat. So we'll leave a little space for them. So that's where energy can go in and out of a system. So what I'd like to kind of do now is I'd like to kind of combine some of these terms together. And we'll start to see where some of the equations on the equation sheet come from. So the first thing I'm going to do is I'm going to subtract UO and KO to the other side. And actually, I'll subtract energy thermal original as well. So what am I left with? I've got work and heat, and that equals UF minus UO plus KF minus KO plus energy thermal final minus energy thermal original. So we have work plus heat is delta U plus delta K plus delta E thermal. So we have a very different looking equation, but I'm hoping you see it comes from the same basic idea you've been working for about a year on at this point. So here's the deal. In general, the thermodynamic systems we're going to be looking at don't have a large change in macroscopic potential or kinetic energy. We're typically not taking our engine and like dropping it off a cliff or making it go faster. So we don't usually have, at least in the simplest forms, macroscopic changes in these. So what we're left with is work plus heat is the change in thermal energy. Could you guys pull out your AP equation sheets and see if there's anything like that on there? They call this change in internal energy. And basically, this is what our textbook calls it. This is what our AP calls it. And this is not potential energy. This is internal energy. This equation really tells us a couple things. And it's one we can use both on the conceptual level, but also on a quantitative level. And basically what it's telling us is the way to add energy to a system requires a transfer of heat, work, or both.